pleasure to be here because I've been following what D-Wave has been doing for the last 20 years, basically since my early undergrad. And today I'm going to talk to you about how we can use it for crystal structure prediction. Right? But let me remind you first, what are the crystals? So you have an example at the top right corner, right? So this is a material which is known as lithium cobalt oxide, and I carry it every day with me here. So that's my phone. So it's inside of this battery. And crystalline materials are characterized by long range order. So if you look at the layers here, right? So there is a layer of lithium, there is a layer of oxygen, and so on. They are well arranged. So long range order, crystalline materials, right? Obviously, batteries are not only in the phones, they are also in cars and so on. But crystalline materials, their use cases go beyond that. I mean, they're very important for our oil-based economy. So, that's the old version of a slide, but okay. So I would just remind you, catalytic converters, they rely on the catalysts, I mean, green hydrogen and so on, so lots of manufacturing depends on the catalysts, but also they are used in solar energy, which is basically very important to us nowadays to sort of build resilience towards oil supply shocks and so on. Okay? So how do we actually discover new materials? I mean, traditional way would have been some kind of trial and error, but nowadays we are shifting more and more towards computation and automation. Right? So we rely on computation and databases to do good suggestions about the compositions to look at, chemistries to explore, and so on, good for function. Then, given the composition, we try to predict the material that will be formed in the lab if we try to synthesize it, right? So this is the problem of crystal structure prediction. We say, okay, given the atoms, given the chemistry, what we will form. And then, we use them when you have structure, because structure-derived properties, right? So you could assess them and figure out whether they're good for some function or not. Okay? And then it goes into evaluation, right? So experimental evaluation now more and more relies on automation. And then it goes back. So you have this loop. So in Liverpool, we work actually across the whole discovery spectrum. I call it bin to cup. But today I'm going to focus specifically on crystal structure prediction, right? So how can we predict structures of crystalline materials? Okay? And you can actually approach this problem from many different perspectives and angles, right? But I really like this one, which is based on optimization and our physical understanding of the world, right? So we know that the atoms should form an arrangement which minimizes their interaction energy, right? So this is what typically happens. And then the problem of predicting what kind of structure we would observe is actually an optimization problem, right? There are two main challenges here, right? The first one is actually how do you compute this energy? Because it is based on quantum mechanics, right? It's hard, and I'm pretty sure there are many people in this audience who know exactly how to do that and how quantum computers could help with that, right? So this problem received a lot of attention. But when you talk specifically about discovery, it's not only about simulating what you've got, but it's also about discovering, right? So you basically need to go through many atomic arrangements and identify the ones which are of the lowest energy, right? And this problem is way less studied, right? And so the purpose of my talk today is to actually focus on this part and explain to you how we can actually do that. I would actually, because it's a research talk, I would entertain you with a few formulas. There will be 2 high-level technical slides, but I mean, how do we actually, it's not too difficult in my view, so we can, you can all follow. So imagine you need to put atoms in space somehow, right? Find their lowest energy configuration. What would you do? I mean, we've seen the talks today, you need to discretize the space somehow. You say, okay, my atoms could live in some specific locations in the space, right? Then there is a finite number of them. In principle, you can go through all of them and brute force them. But you don't want to, right? You want to use more clever methods. So now you have this problem, and you want to turn it into from a problem in chemistry into a problem in computer science, right? So we rely on integer programming, what is known as a canonical class of optimization problems. So we go from the crystal structure prediction to integer programming, right? So the way you do it, you introduce binary decision variables. You basically say, well, if a given position is occupied by a given atom type, like strontium lives at position 0, then my decision variable x is actually 1. If it doesn't live there, it's 0, right? So you have this decision. And then you would put some constraints on top of that. I would talk about them on the next slide. And after that, if you can express your energy as a certain function of these variables, you basically have your optimization problem. You can use various tools to do that, right? So you start, you kind of live in the world of computer science. Okay. Now, I would be, just because there are experts in the room, this is a very specific slide, but I don't think I have more, there would be complicated formulas later on. So, but I wanted to just be very specific. So now, what kind of constraints we're talking about? Well, we talk about natural constraints, which is exclusivity, right? So you're not allowed to put two atoms on top of each other, so that's one constraint. And another constraint is related to chemistry. What kind of stoichiometry you're getting, right? So what kind of atoms you're allowed to use? On this example, I'm allowed to use 3 atoms of oxygen and 1 strontium and 1 titanium. So that's the formulation. And the important part is actually energy. How do we model energy? So in our original work, published a couple of years in Nature, it was relying on classical force fields, right? Think about it as an electrostatic interaction, Coulomb potential, and some kind of repulsion forces between the atoms, sort of like Buckingham potential. So, and if you rely on them, they're actually two-body interactions, and if you express this energy in terms of these variables, it becomes a quadratic expression. And actually, these constraints are pretty easy. That's a standard trick to actually put them in as quadratic expressions as well. And if you look at this very long and scary expression at the top, you would actually see that it's a function which is quadratic in terms of variables, and the rest are fixed coefficients. Okay? So it means we are dealing with a quadratic, unconstrained binary optimization problem, which is perfectly suited for D-wave quantum annealers, right? So, and that's what we've done back in the day. We did a few simple trial cases and predicted them and said, okay, maybe we can actually use quantum computers to solve structure search problems and material discovery problems. But then there is a big problem here. Well, big. There is it's simply because we use it in practical setting, right? So classical force fields are not widely available. So they're well studied, they're available for some systems, but not across the board, right? And we want to simply be able to just run it, just do our experiments with people in chemistry, identify interesting structures, right? So what do we want to do here to address that? Well, we need to rely on the data, right? So we need to come up with a machine learning style method and data-driven method that would allow us to model interactions between the atoms in such a way that we would still retain the ability of using D-wave quantum annealers, but at the same time, we would do it at scale and do it across all chemistries. Okay? So the idea that we came up with is to actually look at the interatomic distances in existing materials to sort of derive how they should interact. And I would actually show you how it's done, right? So a colleague of mine took nearly all materials existing in the known to mankind, right? Did a lot of filtering and pre-processing, and that based on this big data set of structures, he can actually select now if you're interested in how titanium and oxygen should interact, he would say, okay, let's look at these structures and observe how atoms are allocated against each other, right? So then you can simply do a histogram of this is the distance between the atoms, right? So titanium and oxygen are at a given distances, right? And then you do it for every structure, and then you average this out. So you get a histogram of that kind, right? So that's where atoms like to be against each other, right? So it could be like 2 angstrom away or less, and so on. So this kind of weird function. So if some of you did physics, you probably would think, well, it reminds me of radial distribution function, and it is kind of the same concept. And finally, in order to still get some kind of energy score, because we want to have energy, we apply minus log n transform, and then we get a potential like this, right? So what we have done here, we have replaced the original objective function, which is based on the classical force field methods, models, with a new one, right? Which is coming from data, right? And the best part here is that now this one is available across most chemistries. And it could guide quantum annealers still, right? Okay, now you probably would wonder how it performs, right? So the first thing is, well, would it be able to predict, is this objective suitable for structure prediction, right? Because we did a bit of modeling, we need to double check that. And then the second part is, well, would D-wave quantum annealer be able to handle that, right? So, and we did our experiments, and we did them with the premise of actual evaluation. So we didn't, before we tried some toy examples, and in this case what we did, we said, well, let's try to evaluate it in the same way we evaluate any other CSP method we are coming up with, right? And then the results are more or less as you would expect, right? So if we start looking at sort of smaller structures and smaller problems, we get quite a good success rates, right? So we can recover them pretty quickly. So if we start looking at problems which are larger, our success rate goes down because they are harder, they are bigger, and so on. Here, I would like to remind you that while, I mean, the numbers look small, any of that actually takes seconds anyways. So we are quite happy, and that's what people in chemistry often tell me. Because I'm a computer scientist, we are all about efficiency. If it cannot run on your laptop, then that's a bad algorithm. You need to make a new one. People in chemistry usually tell me the different thing. Well, if it cannot run on a supercomputer in a few days, then it's a problem. But before that, don't even think about it. So it's a kind of learning point. So it still takes seconds. And if you go to even larger structures, then we actually have no success. Another important reminder here is that the problem itself, we talked about suitability, right? Because it's actually, if you look at the objective function, it is fully connected, and there is a lot of interactions there. So D-wave must embed it into our own architecture. It's actually not ideally suitable for the D-wave quantum annealer. But that's why the company is working on hybrid methods, right? So if you simply call a hybrid solver, then there is no problem. You can still do this job in 4 seconds, right? So it allows you to mitigate some of these issues, right? So, but in many ways, it's a work in progress. We haven't optimized it for D-wave specifically. We just taken our modeling and applied it here, and we can actually do our predictions. Okay, so what did I tell to you today, actually, in one slide? So one thing is that we can frame optimization problem, material prediction, crystal structure prediction problem as an optimization problem, right? And by relying on that, we can actually empower it with a data-driven and machine learning methods. So we can combine both of them, and actually we can use D-wave quantum annealer to predict new materials, right? The ones that haven't been discovered yet. And we hope that it would allow us to overcome combinatorial challenge that arises in this problem, right? And if you really want to abstract it away, like fully, then the way I tend to think about it is as follows. So by using these mathematical reductions, you actually take any kind of chemistry that we have, and we map it to an Ising machine, right, to the D-wave quantum alien, to this type of specific physical interaction. And then we use it as a resettable chemical lab, right? So hardware implementation of D-wave becomes a lab that you can probe with chemistry, any kind of chemistry, look what you are getting, and then get the results out for future evaluation in the actual experimental facility, saving some time. Okay? As usual, thanks for our founders, thanks for D-Wave, for range and access, and big shout out to my colleagues in Liverpool, especially to Asma Kurban, who actually was supposed to deliver this talk today, but unfortunately she couldn't come for family reasons, but she actually spent a lot of time making this project happen. Thanks a lot for your attention, and I've saved you a little bit of time for the coffee break.